All right, guys. So the lab is basically the same thing as the tutorial 1, but you need 2 separate reports for each of them. Okay, and you need to prepare these ones for the quiz next Thursday. So the labs and the lectures, they are in different places. The lectures are here, the labs are in the electronics lab downstairs. We cannot, even though sometimes they are very similar, you guys are doing the same thing, but we cannot stay here forever. Sometimes they have other teachers are teaching here, so I have to move downstairs to the lab. So today you guys are going to have a lab from 2:30 to 5:30, I guess, okay, 5:30 or so. So next Thursday, I'm going to give you a quiz. So the format will be, I already told you guys, but some of you were not here last time. So I'll stand behind you and ask you about 5 to 6 commands, or probably 10 commands of Vim, and to let you operate on your computer. So I'm going to grade your operation based on the performance. Okay. So this is one of the main purposes of the lab. So this 1 hour and 25 minutes lecture is not for the lab, okay? But you'll practice it in the afternoon today. So I want to cover some basics of Verilog from tutorial 1. And so the report of tutorial 1 is due next Tuesday. So there are several things I need to clarify with you guys. This can be a little bit different from other programming languages. And again, I think I would just want to motivate you guys to learn more about this topic, because this is one of the 3 most important computer engineering courses in the curriculum. Even though sometimes it can be tedious, but they are just super important. I didn't receive this type of education when I was in college. So I think you guys are lucky, and please spend more time on it if you can. All right. So basic concept of Verilog programming, you are actually making chips using Verilog. How these chips are being made. So when you are starting a .v file, you can name it whatever you want. You start with a module, and followed by the name of the module. For example, it's the Ungate. And then the ports. So these are the ports. That's the name of the module. A module is literally a box, a black box. Whatever you have in there, it has inputs and outputs. These are the only things are being communicated with the outside world. And these are the ports. For the Ungate, you have in, you have out. Whatever you want to name it, doesn't matter. I just name it in out. You can name it AB, ABY, whatever you want. Okay, and eventually it's going to generate, for this Ungate, it's going to generate a module, which is a device, has the Ungate inside, and has these ports being connected to the input out and output of the gate. It can be A, B, Y, for example. So you have to declare that, since you name it as in and out, doesn't matter. It doesn't mean that the Verilog, the EDA tool, knows which one is input, which one is output. You can declare this name as the input. You can declare this one as the output. But usually we don't do that, right? So you have to write below that module declaration. You need to let Vivado know which one is input, which one is the output. So in is input, and output is out. The out port over here is the output port. All right. So ports are already declared. What's next? The logic. Is there any problem with this program? You need an in one, because the AND gate has 2 ports, right? They can separate the same type of ports using a comma. In one, comma, in two, semicolon, output, out, semicolon, and then directly assign out. So I have to type assign out, which is in one and in two, semicolon, and that's it. That's everything about this module. You need to type end module to wrap it up. So it has to start with module, has to end with end module. So it knows that everything here is within that device. It's a chip, or it's a logic block. Yeah. Okay. And I have a lot of examples on the website regarding the operators, the logic operators. You can definitely look into that. Here's just a general review of everything. Okay. However, this is just a chip. Okay. There's no signal. When you're trying to simulate it, you need a test bench. Which is also a .v file. You couldn't even tell the difference. It has modules. It has a module and end module. So all the Verilog code is being included in between these two statements. So when you are writing the code in the test bench, you start with module as well, because it's also a .v file. You can name it whatever you want. Okay, for example, I name it as AND gate underscore TB, the test bench. It doesn't have any ports of the test bench because I'm not using this for the IPGA board. It's just for the EDA, the Vivado simulation. Because the signals, when I'm doing a test bench, I'm actually wrapping this device into that test bench. So you can imagine the test bench is another layer. Okay, so this AND gate here is being instantiated in this test bench, because in this test bench module, I haven't written all the other things, but I will instantiate first. For example, I have to use exactly the same name over here to instantiate. So it's called AND gate, and I just name it UUT. It's a unit under test, and I'm going to make the connections. Right. But in the test bench file, I need 2 signal lines and 1 signal line here as inputs and outputs. So I'm going to name this as A, for example, just make it simple. And this as B, this as Y as well. You don't have to name it the same name as the ports of the instance. Okay, it can be anything, but I just name it as ABY. I give you another example from yesterday's lecture, so you can actually, no, Tuesday's lecture. You can look at that one as an example as well, but this is a little bit different. I just name it the same name as a submodule's name, port's name. So now I'm going to make the connections. So this test bench has ABY, and these are not inputs and outputs because I'm not connecting the test benches ports to anywhere. I have an IPGA, yes. So the IPGA board has switches, has LEDs. This can be used as, so switches can be used as inputs, because if I switch it down, it's sending a signal to the chip. 1 or 0, doesn't matter. The LEDs are inputs or outputs. Output, because they cannot send signal from the LED. It's receiving a signal and indicate if it's a 1 or 0 over there. Okay, So the LEDs on the board can be used as outputs, and the switches on the IPGA board can be used as inputs. However, I'm not doing IPGA emulation yet. It's for next week. So we are just doing simulation. So the simulation is everything in the EDA tool in Vivado, and it's going to inject a signal to there. So I don't have to declare any ports for the test bench. These are just signal lines. And these signal lines are different data types. So you will be used to these different data types in the future. But now I just let you know. For A and B, I'm going to use a register type. For Y, I'm going to use a word type signal line. And why is that? Because when I'm running the simulation, I have to assign signals to A and B as an input. For example, I start assigning the signal. It's the initial begin. That's how you start assigning signals to the signal lines. And initial begin and end. You have to wrap it up using begin and end. So initial, begin, and end. So this statement, this block, will only be executed for once. Keep in mind, initial, begin, and end. So whatever in there will only be executed for once after you run it, after part it up. So it's actually assigning an initial value to A and B. So whenever it's receiving initial value assignment, they have to be registers, actually diffie flops, to memorize that value. So they have to be reg or register type. Let's see. So for whatever here, okay, I'm gonna zoom in. If I do a 5 nanosecond time delay at the very beginning, and then I'm gonna assign A is a 1-bit binary number and the value is 0, and B is 1-bit binary number is a prime, it's a 0 as well. That's the first assignment. And then I delay it for another 5 nanoseconds. Why is 5 nanoseconds? Because you have to have that time scale on the top of the test bench, which is a different prime. So this prime is not the prime beside the semicolon on the keyboard. It's the prime on the left top corner of the keyboard. Left to 1, number 1 key, okay? Time scale 1 nanosecond / 1 picosecond. So the resolution is 1 picosecond. And the time scale is 1 nanosecond. So which means whenever you have a 5 years, 5 nanoseconds. And the resolution is 1 picoseconds. That's the smallest time it is able to resolve. Here's the time unit, which is 1 nanosecond. So I assign this for 0, first, and then I'm going to assign 0, 1, and then delay for another 5 nanoseconds. I'm going to assign 1, 0, and eventually I'm going to do a 1, 1. So this will allow you to explore all the possible combinations of the 2-bit input. It's a 2-bit binary number as an input. So 0, 0, 0, 1, 1, 0, 1, 1. All right. You are thinking, can I just directly write a 0 here instead of 1 prime B0? Yes, you can. But usually this is a better practice since you are telling the system how many bits are there for that 0. Is that 8-bit, 8 zeros, or just 1 0? Okay. All right. We haven't made the connections here yet. So we instantiated the AND gate from here. So we are including that AND gate into this test bench. That's how it is doing that. I have to instantiate it, so it's being included into this test bench, which is this .v file. All right, just not making any connections yet. How can I make the connections? So just in this parenthesis, dot. So the signal line right behind the dot is a signal from where? From the UUT or from the test bench. You have the signal line A from the UUT, unit under test, and also the signal line A from the test bench, right? So one more question. Are these the signals from the test bench or from the UUT? Test bench. Since you are assigning values to it, it's like the function generator of voltage you can give to that test bench or the breadboard on the bench, right? You're injecting signals to these signal lines. So now you can see why this one can be a wire, why this two has to be rag. Whenever in the initial begin, you are assigning an initial value to that signal line. See, you're assigning this to here. You're assigning this to B. You're assigning this to A, assigning this to B. Did you see anything like is assigning something to Y? No. In initial begin? No, it's the output. I'm not assigning anything to it. It's directly being generated by the logic circuits over here. So that's why this one can be a wire, and this one, these two, have to be a register type because it's receiving the signal, it has to memorize it for a certain period of time. This can be confusing for a few weeks at the very beginning of the semester, but in the future you'll be used to it. Okay, then how to make the connections between the test bench and the device itself in the parentheses in the test bench. Right after you initiate it, how to make the connections. So it's going to be dot, and the signal line right behind the dot, keep in mind, right behind the dot is the signal from the UUT, from here. Dot A, parentheses, so A is a signal line from the UUT is being connected to where? To A from where? The test bench, which is this signal. I'm making the connections. Yes. So just in case this is a special example because they are the same name, all right, you don't have to make them the same name. Sometimes with a very simple example like this, I think it's good to have the same names. You don't have to think about which one's from the UT, which one's from the test bench, just the same names. Just dot A, parentheses A, dot B, parentheses B, dot Y, parentheses Y, done. Comma, all right, dot B, like I said, parentheses B, comma, oh yeah, I do have in one, in two out here, okay? But I'm looking at this one, so it's ABY. I'm confusing, I'm sorry. You're right. I'm looking at this one, but I had different names over here. Sorry, just imagine like I have ABY here, okay? But if we're not looking at this drawing, if we're instantiating this device, which has in one, in two, out. So which one should be in one here? Here or here should be in one. Right behind the dot should be in one. Keep in mind. So right behind the dot should be the signal line from the instance or from the device submodule and being shorted to A. And into dot into being shorted to B. So keep it consistent, still looking at this one. So it's going to be a dot Y being shorted to Y. Okay, so I have made all the connections. Do I need a comma after this one? No, it's done. Just parentheses. Okay. Is that clear? Any questions on this? No. And click the run simulation. You can definitely create a waveforms for this one. Another thing you need to know So what if I have multiple modules? So you can have, for example, this is one .v file. This is one .v file. I can have module and gate and module. Okay, I can have all these things over here. Still within the same .v file, I can have another module, which is Xor Gate, and module. Right, you can have the OR logic in there. And you can have as many as you want. Doesn't matter. Or you can have separate .v files. Only has the AND gate. So the names of the V file and the module name or the module can be the same, can be different, doesn't matter, depends on how you want to name it. Nobody cares. Just for the AND gate. And I have another one. Have the logic here. Either way, nobody cares. So when you are instantiating these modules in the test bench, it's another .v file. What actually matters? This name, this name, this name, or these names. So you are instantiating the submodules over here in the test bench. Which name you are calling actually? You are declaring. So again, you have several ways to make these modules. You can have a test.v, whatever you want to name it, and have all the module names over here. These are just all the different gates or different logic blocks. Okay. Or we can have separate module files. There are separate .v files to have every single module in each .v file. Whatever you want to do. In the future, I just want to put them together. Okay. For example, I have one test bench. I have a block here, one block here, one block here, 2 input, 1 output, 2 input, 1 output, 2 input, 1 output, whatever. It can be multiple inputs, multiple outputs, but this is one test bench. These are all these modules from here. Okay. So when you are instantiating these modules in the test bench, which name you are calling, or which names you are calling? The file's name, the separate file's name, or the module's name? The module's name. So these are the names really matter, not the file's name. So you are thinking, just to put all the .v files, including the test bench.v file in the same folder, and I included all these files into Vivado. I run the simulation. How does Vivado know which one I'm calling? They're within separate files. How test bench knows? There are separate .v files being opened up separately. It is just able to read the inside contents of the .v files and find out the module names and being instantiated over here. So I'm going to instantiate a module here and gate, and it's a UUT and blah blah blah, make the connection. And same cases for the other ones. UUT or UUT something else. That's a question. Okay. So in the test bench, I'm instantiating different modules. AND gate, OR gate, Xor gate, for example. Do I need a different name for the UUT? Yes, you do. Have to do that. It doesn't have to be UT, it can be UT, UTT, whatever you want to do, but they have to be different names. Okay. Another important thing. So you instantiate different modules in the test bench, okay, by doing that. Xor Gate, for example, UUT3. I haven't made the connections yet. So which means if I instantiate all the gates inside the test bench, so here's the test bench, which means I placed all the individual chips on the breadboard. For example, you have a pretty big breadboard, like the test bench, and just plug in a chip here, AND gate here, OR gate here, XOR gate here, and it is ready to receive signals and being probed as well. So again, this is not on the IPGA, so I'm doing simulation. So there will be ports, not ports, but signal lines over here from the test bench as well. And you want to make the connections. It's straightforward to make the connection from here to here, right? Is this A? Let's make it a different name, AT, BT. So these are the A and B's in the test bench. How do we make the connections? Let's just, for example, just for this one, I'm not going to connect all these ones, but it's going to be the same thing. So how do I make the connection from here to here? Where should I do it in the test bench? Yes. So here, right? If this is the AND gate, that's AND logic. It's going to be dot what? No, dot A. So the instance signal is right behind the dot. So A is being shorted to AT. That's the signal from the test bench. Dot B being shorted to BT. What about these? Let's name it A2, B2. If I have to make the connection from here to here, for example, for some purpose. These are different instances in the test bench. One more thing before we move forward. So I have AT-BT here, so I need to declare them. Okay, and you can imagine in the future I'm going to inject signal into AT-BT for the simulation. So what are the data types for AT and BT in the test bench? Okay. Yes, we have been doing connections between instances and test bench in the parentheses, which is easy to do. However, how do you make the connections in between the instances inside the test bench? Yes. It's like you have a breadboard, right? You grab AND gate, plug in, OR gate, plug in, XOR plug in. If you need connections in between the chips, just grab a piece of wire, just make the connection. So it's easy, but how do you implement it? So declare a wire, let's call it W1. You're imagining that when you're doing that, there will be a floating wire flying into the EDA tool. It's just a floating wire. There's no connection yet. It is a floating wire in the test bench because I declared it in the test bench. It's not a wire somewhere else. Then what? In the AND gate, for example, this is the OR gate. Okay, in the AND gate, I will do a dot Y, which is output, and make the connection to W1. So it's gonna do that. Okay. In the OR gate, I'm gonna do a dot A2 connect to W1 as well. It's going to do this. All right. So I'm actually indirectly connecting Y to A2 by connecting both of them to W1 in the two instantiations. Same for all the other ones. If you need connections inside the test bench, just declare wires and connect both terminals to individual devices. Make sense? All right. One more thing on tutorial 1. Here. So this module is not a simple AND gate or OR gate, it's just a module. It's a test 1, it's called test 1. And has how many ports? 4. And these are the inputs, these are the outputs. Okay, you can define them, declare them right below it. And assign, it's just a very simple combinational logic. It's in one into whatever. So Xor gate, the Xor operator has a lower priority. So you're actually doing AND, OR, and then Xor. Okay. And for this is for output 1, for out 1, for that signal line output. And for out 2, it is simply just the inverse of in2. That's an inverter. That's a not sign here. It's not. Okay. But it's going to delay for 20 nanoseconds before it makes that assignment. Okay, that's the logic. It's just not for any purposes, just for simulation, for practice. And then let's look at the test bench. Can't read it. Barely. Okay. It's a very similar syntax. It's a module, but doesn't have any ports. It doesn't mean that you don't need the ports for the test benches. It's just we are not implementing this on the IPGA. So we are not using the clocks, the switches, and LEDs for the test bench. These are just the internal signals being directly injected into the sub-module or the unit entered test. So see that we have reg, register type signals as the input and wires as the outputs. Since we're just simply probing these outputs, not assigning any initial values to them. And now instantiate test 1, this module, which is here. It has to be the same name in order to instantiate it. And name it as UUT. It doesn't have to be UUT again. And parentheses to make the connections. Right? Dot. So the signal line right behind the dot is a signal from the instance. And the signal here is the signal from the test bench. Out2 test bench, in one test bench, into test bench. Just make the connections. And then initial begin. Keep in mind, I just mentioned that for the initial begin and end for this block, it's only being executed for how many times? Once. Okay. There are initial values. However, if you want to run some of the statements for longer time, for more times, you can have this statement over here, repeat 4. It's going to repeat this single line for 4 times. But the whole thing here will be only executed for once. So in that case, these will be executed once, but this will be executed for 4 times. Not 8 times, not 12 times, 4 times, all right? by looking at this one. So this is not a, this is a curly bracket. Keep in mind, just by looking at the website, just be careful about it. So you can use a curly bracket to combine these binary bits into one binary number. So for example, in1t, comma, in2t, they used to be 1-bit binary numbers, and now you combine them together, this becomes MSB, this becomes LSB. So 1 here is not 1 anymore, is what? 2. Is that correct? Yeah. It's 2, right? But they used to be 1-bit binary numbers. They were 1-bit. But you have a curly bracket, you can combine them together. So this becomes the 2 binary bits together becomes a 2-bit binary number. And it's adding 1 prime B1. So it's a 1-bit binary number and the value is 1. It's a counter. It's adding 1 for each cycle for 4 times. So it's a 2-bit binary number and adding 1 for each time. Starting from what? So what's the starting number of this combination? 0. Why? You did it. It's the initial begin. It's assigning initial values to in1, in2, in1t, into t. So they have initial values. They should be able to hold that value as an initial value. And you need a latch, D flip-flop. Where cannot do it. Has to be a latch. So that's why in1t, in2t are register type. They're regs. Okay, it's clear? So this will be executed for 4 times, and each time it's going to add a 1 to it, to this combination, to this 2-bit binary number, and being assigned to itself. So it's actually adding 1 to itself. But before doing that, it is delaying that operation for 100 nanoseconds. That's just a simulation. And now let's see. There's a little error here. So this is what I drew, okay? After I had that simulation test bench, you can actually predict what you are going to get. So that's what I drew here. So these labels are a little bit incorrect. So this should be 0. So I should actually shift all the labels to the right-hand side by 100 nanoseconds. So this is actually 0. This is 100 nano. This is 200 nano. 300 nano. Okay, there's a little error here. But anyway, so at 0 nanoseconds, whenever you part up, start showing some signal here. And it's going to plot a dot here as an input to the test bench. So quick question. Whenever you give a signal or 2 signals to the input, are you getting an output immediately as the output? And why? So look at the device here, the test bench. Did you make the connections from the test bench to the sub module? Yes. Did you assign initial values to in1t, into t? Yes. So whenever you short these 2 inputs to the ground, which is 0, you give a 0 or give zeros to these 2 inputs. Since they are physically connected, here, to the inputs of the sub module, are they physically connected to the module? Yes, you did it. You made the connections. Let me do it here quick. I don't know what is this device. Okay, it has a different logic. Right. Did you make the connections? Yes, you instantiated these devices and make the connections in the processes. Use a dot something, processes something to make the connections. So they are physically connected. So whenever I assign 0, 0 here, what's going to happen? do you have a switch to turn on and off, just blocking the signal being sent to the sub module? You don't. They are connected. That's it. It's a combinational logic. You don't need to wait for any clocks. Whenever these values are here, there will be a little time delay, but in the simulation, it's ignored. So whenever you assign values here, what's going to happen to here? Or do you know what's the value here will be? Yes, it's a combination. It's like AND gate. Whenever you give 0, 0, boom, 0, no doubt. So if you look at this one, initial begin. After I run the simulation, initial begin is going to be executed, and zeros will be assigned to the inputs of the test bench, which is, so the inputs of the test bench are physically connected to the inputs of the device because of this, right? So you are expecting outputs, are you? Yes. Because this device defines the logic of it. The inputs are here, so definitely you can get all one. And since you have the input for in2 as well, so you are getting out2 as well, but it's being delayed for 20 nanoseconds. Okay, so that's why at time 0, this should be 0, and you are having 0, 0. This logic is going to give you 0 for all one, and 20 nanosecond delay is not doing anything. But after that 20 nanoseconds, it's going to plot the point over here, which is 1, because it's the inverse of 0. So this is what this is going to do for the result, simulation result. And right after that, it's going to delay. It's going to delay everything for 100 nanoseconds. And how many times this time delay will be executed? Once, because still within that initial begin block. Okay, so look at the drawing here. So after that initial begin assignment for 2 zeros, yes, you are immediately getting outputs here. It's going to be delayed for 100 nanoseconds. Right after that, that's 100 nanoseconds. What about this one? Why this stops at 100 nanosecond, not 120? Why this one is shorter? Yes, there is a 20 nanosecond delay, but why this one, this L2, cannot enjoy the whole 100 nanosecond simulation? Has to stop. So actually this value is only being assigned for 80 nanoseconds, but not 100. So the question here is why this is not being extended to 120 nanoseconds to make that 100 nanosecond simulation happen. Okay, so by looking at the device here, so this is a sub module, that's the logic, right? That's a sub module, that's the instance. So it has a 20 nanosecond time delay internally. That's why you are getting this. However, for the test bench, I only defined 100 nanosecond simulation. So whatever happening inside that sub module, it's your problem. It's not my problem. It's your problem. You can do whatever you want. You can even delay it for 100 nanoseconds. So you're not doing anything. I'm the person doing experiment. I told you that. I told the circuit that I'm just doing 100 nanosecond simulation. Whenever the time is up, it's done. You can delay whatever you want inside. It's not going to affect my simulation at a higher level. Does that make sense? So that's why no matter what this sub module is doing for that signal line, it's going to stop at 100 nanoseconds for the simulation. Okay, you can delay for 20 nanoseconds, you can delay for 30 nanoseconds, I don't care. Okay? At 100 nanoseconds, when time is up, I'm going to stop. Because that's what is defined at a test bench. This is a signal being injected into the device. I'm going to stop right after that. So yes, this will be only be executed for once, and then it's getting to the repeat session. But before it make that combination of the two binary bits, it's going to delay the whole thing for 100 nanoseconds. So by looking at this drawing here, all right, we work here, right? We work here. So nothing is going to happen until the first 100 nanosecond delay. It's here. So this 100 nanosecond delay is this one. And after that, it's going to do the operation. So this one doesn't have any extension in the time domain. It's just assignment. It's going to plot a point after that time delay. So you may have a question. If this one is only plotting a point, how can you visualize the extended result or logic in the diagram? So see here, 100 nanosecond time delay, okay? And after that, plot a point here. But this has a 20 nanosecond delay inside the module, so that's why it's not plotting a point yet. It's going to wait until here to plot a point. So after it plots the point, it sets that voltage level at that point, and then whenever it runs the second time for this repeated statement, it runs 100 nanosecond delay first, right? That's why this one is being extended. So you can see that signal line here. This is the 100 nanosecond delay. Until here, it's going to plot another point and then extend it. And then plot a point, extend it, so on and so forth. Okay. Does that make sense? Not really, seems like. All right. That's why if you look at the simulation result, in the very beginning, there's a 20 nanosecond delay, which is red because nothing is being assigned to anywhere. It's called high impedance. It's actually nothing. It's right in the middle. Usually just show you it's not high, not low. It's just 2.5 volts if it's a 5 volts logic. And the following curves are exactly the same as what we just analyzed over here. That's how that works. So this teaches you how to use time delays to simulate a circuit and observe the result to verify the logic. For the first system module, that's another example here. And to let you guys know another concept. So if you have one device, two devices, there are sub-modules. And I have another module called first system. Do I have to make this first system a test bench? No. You can have as many layers as you want. This can be another module, but which includes other 3 sub-modules. And you can have another very similar thing here, and eventually you wrap them up in one test bench and feed the signals in there and make the connections using wires. So you can have as many layers as you want. You can instantiate a first system which has other sub-modules in it in the test bench. Okay. This is how it works in real world. The CPU probably has over 100 levels. Okay. Anything else you need to know? So see, this first system module is not a test bench at all. It has all these modules and use wires to make the connections. And this first system can have its own inputs and outputs to interface with your test bench in the future. Right? That's what I want to tell you guys. Any questions? Anything? So in the very beginning, it's a new language. It's the same as you are learning a new natural language as well from a different country. It can be difficult at the very beginning, but Verilog is actually very similar to C++ or C or MATLAB. So it's actually easier, a lot easier compared to learning a totally different language. Whenever something is difficult, that means it's also very rewarding. And especially for digital design tools like this, it's a universal design language everywhere. If it's serving for nothing, for no sense, then I won't take my time to learn it as well. But any single statement, any piece of knowledge you're learning here can be directly converted to dollars, actually. Some kind of the first salary in your bank account after you graduate if you got a job in digital design. So these things are directly being used in any companies doing digital design, or some of the companies are doing mixed signal design, analog, digital, but they still have to use FPGAs and Verilog. So it's totally not wasting your time, not even 1 second. Every single second you're spending in this class, every single pain you're taking in this class is rewarding. So take the pain and get a job. It's important. Just let you guys know this.